Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. So we're going to talk about the harmonic bundles. I think it's kind of advanced topic in plane geometry, but it will be great helpful for us to learn about the projection geometry and also learn about the other concepts. So let's start. First, we give some definition here. In line segment AB, let point C on segment AB, point D on the line AB, but out of the segment AB. Okay, so we have segment here. Let's call it AB. And we know that C is inside of the AB and D is outside of the AB, right? So if AC to BC equals to AD to BD, for example, D is here, AD to BD. Based on this figure, we know it's larger than 1, so AC to BC should be larger than 1, right? So I put C here on the right side of the middle point. So if AC to BC equals to AD to BD, then points C and point D divide the segment AB in harmonic division, right? And then we call ACBD a harmonic range. Okay, so if we use the directly line segment concept, right, then we can assume that this is a positive direction. This would be the negative direction, right? Then we know that AC, the AC, that's a positive segment or vector, right? And BC would be negative, right? So AC to BC times, let's do this, divided AD to BD. See, AC to BC, they are in the opposite direction, and AD to BD, AD and BD are in the same direction. So this division gives -1. That can also represent ACBD in harmonic range or harmonic set, right? Okay, that's the definition here. And now we think about the properties of this. So let's call this line L, right? Line L, in line L, let CD divide the segment AB in harmonic division, and M is the midpoint of AB. We just set M as a midpoint of AB. Then we think about several properties here. Okay, the first one, points A and B divide segment CD in harmonic division. What does it mean? It means that if AC to BC equals to AD to BD, then CA to DA equals to CB to DB. Right? If AC to BC equals to AD to BD, then CA to DA equals to CB to DB. So we compare these two. We can switch CA to here, right? Then we get directly that DB, right? DB to DA equals, so we can start from this one rather than from the conclusion, right? If we start from this one, we just put the AD down here, swipe the AD and BC, then we get AC to AD equals to BC to BD, right? Which means CA to DA equals to CB to DB, right? So that is saying if CD divide AB in harmonic division, then AB divide CD in harmonic division. Okay, that's first property. And the second property, we want to prove that 1 over AC plus 1 over AD equals to 2 over AB. Think about that. This is our problem set. We have AC here, we have AD here, we have BC, BD, but we don't have AB, right? So we have to break AB. Then basically we want to prove that 1 over AC plus 1 over AD equals to 2 over AC plus CB, right? That is AB. So basically we want to prove that AC plus CB to AC plus CB to AD equals to 2. Right? And AC, so for this term, it's 1 plus CB to AC. We know that CB to AC equals to BD to AD. Right? So we can change it to BD to AD plus AC plus CB to AD equals to 2. Which is AC plus CB plus BD equals to 1, which is obviously true because AC plus CB plus BD, that's AD to AD equals to 1. So this is true, right? Property 2. Property 3, that AB times CD equals to twice of AD times BC, right? We want to prove this one. Still, this is our problem set. We don't have the AB here, so let's just break AB into AC plus CB times CD equals to, we don't have the CD here as well, right? So here we don't have CD, so we break the CD into CB plus BD. Right, that is CD. We want to prove that it equals to twice of AD, which is, yeah, just keep it there, AD times BC. Right, we want to prove this basically, and equivalent to AC times CB plus, just want to confirm, yeah, AC times CB plus AC times BD plus CB times CB plus BD equals to twice of AD times BC. Right, and we see here AC times BD that equals to AD times BC, so cancel one of them. Then we basically want to prove that CB times AC plus CB plus BD equals to AD times BC. And we know this is AD, so this is true. Right, that's for property 3. And let's check on property 4. Remember, our problem set is that AC to BC equals to AD to BD, right? That's our problem set, and we want to prove that, let me just draw it here. So A, B, C, D, M. For property 4, we want to prove that CA times CB equals to CM times CD. Right, so what is CM? CM is, so equivalent to CA times CB equals to Cm, that is Bm minus Cb. Bm is half of AB, so AB divided by 2, which is Bm minus Bc, right? That is Cm times Cd, right? And what is Cd? Cd we want to represent as AB by half BC times CD. CD is BC plus BD, right? Yeah, so we use this one times 2 to the left side. So basically we want to prove that twice of CA times CB equals 2. Twice of CA times CB equals 2. AB minus 2BC times BC plus BD, right? So we have AB times BC minus 2BC squared minus 2BC plus, plus AB times BD, right? So we put all the BC term to the left side, which we get 2CA minus AB plus 2CB plus 2BD. Excuse me. Times BC equals 2 AB times BD. That's basically what we want, right? And look at this term. So twice of CA plus twice of CB, that's twice of AB, right? Plus twice of BD, that's twice of AD. So it's twice of AD minus AB times BC equals 2 AB times BD. That's what we want to prove, right? Basically, we want to prove twice of AD times BC equals 2 AB times BC plus BD, right? And BC plus BD, that is CD. So that is AB times CD. So basically we want to prove twice of AD times BC equals 2 AB times CD, which is property 3. We just proved it, right? So this kind of proof are not very difficult because you can just break them down, and it's just a very, very fundamental algebra. Okay, so for this one we got this here, and for the next one we need to prove that dA times dB equals 2 dm times dc, right? Again, let's put the figure here: A, B, D, C, M. So what is dA? That is AB plus BD, right? And what is dm? dm is MB plus BD. So this thing can be rewritten as dA times dB equal. We want to prove that dA times dB equals 2 dm, which is AB divided by 2 times plus, right? That's MB plus BD, and times DC, right? DC can be written as BC plus BD, right? Similar to what we had before. And now we can see we want to prove twice of AD times DB equals 2 AB plus 2BD times BC plus BD. That's what we want to prove, and we move all the BD term on the left side, so we have 2DA minus all the BD term, right? So here we have AB here, and this is AB and minus 2BC, right? And minus 2BD, right? Times BD equals to AB times BC. Basically, we want to prove this one. And put the AB times BD back here. I think we need to put it back here. Yes. So we have 2DA, right? DA, think about DA minus BC minus BD, which is AC, right? So we have 2AC times BD equals to AB times BC plus AB times BD. BC times, which is AB times CD, right? We still want to prove this one. And this one is same to this one, right? Wait, AC. Yeah, because AC times BD. Because we have AC to BC equals to AD to BD. So AC times BD equals to AD times BC, and twice of AD BC equals to twice of AC BD. So this is still true, right? So that's a property 4. Let's consider about property 5. Right. For property 5, A, B, C, M, D, right? We want to prove that MA squared equals to MB squared, which is obvious. And we want to prove that equals to MC times MD, right? What is MB? MB is AB divided by 2 squared, right? And what is MC? MC is half of AB minus CB. And what is MD? MD is half of AB plus BD, right? Half of AB, that's MB, plus BD, that's MD. So it equals to AB to 2 square minus AB to 2 CB minus BD, and minus CB times BD, right? So basically we want to prove that AB to 2 BD minus CB equals 2. Wait, no, actually AB to 2. So we move this one to the left side, let's make it a positive sign, and here is a negative sign, so we still need to flip it. Yeah, that's true. Minus CB equals 2 CB times BD, right? We want to prove this one. And yeah, that's true. So we need to think about the BD minus CB here. Basically, we know that we can break AB, which is AC plus BC, to move this 2 over here. So this one times BD minus CB equals to twice of CB times BD, right? That's the thing we want to prove. And AC times BD. Remember, AC to BC equals to AD to BD. AC times BD, that's AD times BC. So AC times BD, that's AD times BC. And minus ACCB. plus BC BD minus BC squared equals to 2CB BD. Right, we want to prove this. So we can just keep AD BC here, move all the CB term on the right side, which is AD times BC equals to CB times AC minus BD plus BC plus 2CB, right? So AC minus BD. So AC plus BC, that's AB, right? So this is AB. And plus, it's basically AB minus BD plus 2CB, right? I'm not sure if I go something wrong. Let me just restart this part. Because it doesn't look like correct. Let's just restart here. Excuse me. Right, so let's restart. We want to prove that MA squared equals to MB squared equals to MC times MD, right? And we know that this is true, right? And we already know AC to CB or AC to BC equals to AD to BD, right? So basically we want to prove AB divided by 2 squared, which is MB squared equals to MC times MD. What is MC? That is AB divided by 2 minus CB. And for MD, that is AB divided by 2 plus BD. Right? So we have AB divided by 2 squared, they cancel each other. Basically, we want to prove 0 equals to AB by 2, BD minus CB times BD, right? So we can shift this one to the left side. Basically, we want to prove that CB times BD equals to AB, 2 is here, then AB times BD minus CB. Right, so this term can be rewritten as AB times BD plus CB minus 2CB. Right, so the first one, BD plus CB, that is CD, right? And we already know AB times CD equals to twice of AD times BC, right, from here, from this one. AB times CD equals to twice of AD times BC, so it equals to twice of AD times BC minus twice of CB times AB, right? Now we can put all the BC term together, so basically we want to prove that CB 2CB times BD plus AB minus AD equals to 0, which is true because BD plus AB, that is AD minus AD is 0, okay? So here we prove a very, very important equation, which is MA squared equals to MB squared equals to MC times MD. Right, MC times MD can be taken as a power of from M to a circle, which is passing through point C and D. Right, And mb squared can be taken as the power of m to a circle, which is tangent to this line on the point B or point A, right? So that's ma squared, mb squared, which means this power, right? This power from m to the circle that's tangent to line L on B or A equals to the power from m point to the circle that's passing through C and D, which means m is on the radical axis of these two circles. Okay, that can be useful for some problems. Okay, so let's see the next property. In the triangle ABC, circle I is an inscribed circle of the ABC and tangent to BC, CA, AB on DEF respectively. So basically we have a triangle ABC here, and we find the inscribed circle. Right, so on D, E, F. And EF intersects BC on point P. Right, so let's restart. In triangle ABC, circle I is inscribed circle of triangle ABC and tangent to BC, CA, AB on DEF respectively. EF intersects BC on point P. So we want to prove that BCDP is a harmonic range, which means that we want to prove BD to CD equals to BP to CP. Right, we want to prove this. How can we do that? The very straightforward thing is that we can just use the meaningless theorem, right? Because this is a triangle, this is intersection line, and we have these like BD, CD, BP, CP. That's basically the strong hint. We should use the meaningless theorem, which means that we have AF to FB times BP to CP times CE to EA equals to 1, right? And we know that AF equals to AE, so these two cancels, right? That means we got BP to CP equals to FB to CE. And FB equals to BD, CE equals to CD, so it equals to BD to CD, right? That is saying BD to CD equals to BP to CP. So BCDP is a harmonic range. Okay. Now let's look at a new definition here. If ABCD is a harmonic range, P is not on the line ABCD, then connect PBPCPD. PAPBPCPD is called a harmonic bundle. Okay, so basically it's saying we find a harmonic range here, which is A, B, C, D, right? And P is out of this line, and we call the PA, PB, PC, PD, these four lines, right? These four lines, a harmonic bundle. Okay, Now let's look at the property of the harmonic bundle. The first property is that ACBD. ACBD are 4 points on line L in sequence, right? Basically, it's here. And P is a point out of line L. Then ABCD is a harmonic range if and only if sine angle APC to sine angle BPC equals to sine angle APD to sine angle BPD. Okay? So we want to prove that if ACBD is a harmonic range, then sine angle APC to sine angle BPC equals to sine angle APD to sine angle BPD, right? And vice versa. So let's just think about how to get a sine angle APC to sine angle BPC. Of course, we need to use sine law, right? Here, consider about the area of triangle ACP to the area of triangle BCP. It equals to half of AP times CP times the sine angle APC. And for the triangle area BPC, that's half of BP times CP times the sine angle BPC. Right? So that means the area of these two triangles, the ratio of the area of these two triangles is AP sine angle APC to BP sine angle BPC, right? Which is also can be written as AC to CB, right? That's the area ratio of the triangle APC and triangle BPC. Now think about the area of triangle ADP to the area of triangle BDP. We can return it as a half of AP times PD times the sine angle APD to half of BP times PD times the sine angle BPD, which equals to AP times the sine angle APD to BP times the sine angle BPD, which equals to AD to BD, right? So this is always true regardless of the harmonic bundle concept, right? This is always true. So for ACBD to be a harmonic range, we need this one equals to this one, right? That means sine angle APC to sine angle BPC equals to sine angle APD to sine angle BPD, right? Because this part cancels. For the reverse condition that if this part equals to this part, that means AC to CB equals to AD to BD, which means ACBD is a harmonic range. Okay. That's for property 1. Let's see property 2. For harmonic bundle PA, PB, PC, PD, any line L that is not passing through the point P but meets the harmonic bundle on A prime, B prime, C prime, D prime, then A prime, B prime, C prime, D prime is a harmonic range. This is obvious, right? Because if I want to find another line here, it still has the sine angle A prime PC prime to sine angle B prime PC prime equals to sine angle APC to sine angle BPC equals to sine angle APD to sine angle BPD equals to sine angle A prime PD prime to sine angle B prime PD prime, right? This is true. So that means A prime C prime, B prime, D prime is still a harmonic range. Okay. Now let's look at property 3. Property 3 is very interesting. It's saying for line L and 4 sequence points ACBD that on the line L and point P is out of line L, and in 2 of the following statement can be derived by the other 2, right? We have 4 conditions here, any 2 of them can be derived by the other 2. So let's just do this check here. We have A, C, B, D in sequence, right? P is a point out of it. So let's say if first one and the second one conditions are true, right? If these are valid, and we want to prove that these 2, the third one and the fourth one can be derived by these 2, right? So first, ABCD is a harmonic range. We already know ABCD is a harmonic range, which means that AC to BC equals to BD to AD, right? And also we know that CP is perpendicular to PD. CP is perpendicular to PD. Now we want to prove that PC is angle bisector of angle APB. We know this is 90 degrees, right? We want to prove that PC is the angle bisector of angle APB, and PD is the angle bisector of supplementary angle of the angle APB. How can we do that? I think we can start from using the angle condition, right? Which is, we already know ACBD is a harmonic range. That means sine angle APC to sine angle BPC equals to sine angle APD to sine angle BPD. Right, this is true. And also we know that CP is perpendicular to PD, right? Which means angle APD equals to pi over 2 plus angle APC, or 90 degree plus angle APC, right? That makes this one to be cosine angle APC. Right? And for the angle BPD, the angle BPD equals to 90 degree minus angle BPC, which means the sine angle BPD equals to cosine angle BPC. Right? That is saying sine angle APC to cosine angle APC equals to sine angle BPC to cosine angle BPC, right? So we cross this each other and put them in the same side. We got sine angle APC cosine angle BPC minus sine angle BPC cosine angle APC equals to 0, which means sine angle APC minus angle BPC equals to 0, which means angle APC equals to angle BPC, right? That is saying PC is the angle bisector of angle APB, right? And because angle PBD plus angle half of angle APC equals to 90 degrees, that means PD is angle bisector of the supplementary angle of the angle APB, right? Okay, so that's from 1, 2, we get 3, 4. And all of these can be reversed, which means that we can use 3, 4 to get 1, 2, right? And for the next one, let's consider about 1, 3. See how we use 1, 3 to get 2 and 4, right? So 1, 3 is valid. That means sine angle APC to sine angle BPC equals to sine angle APD to sine angle BPD, already valid, right? And we want to prove that CP is perpendicular to PD, right? Notice that DC is the angle bisector of angle APB. That means this is 1. So 1 equals to sine angle APD to sine angle BPD, right? Consider about here, the angle APD does not equal to angle BPD. Right, angle APD does not equal to angle BPD. That means angle APD equals to pi minus angle BPD. Right, angle APD equals to pi minus angle BPD, which means angle APB equals to angle APD minus angle BPD equals to pi minus twice of angle BPD. Right? That is saying the angle BPD is half of the supplementary angle of the angle APB, which means PD is the angle bisector of the supplementary angle of angle APB. Right, we just proved 4. And if 4 is valid, then 2 is valid, right? Because we know that these two angles are equal, and this is a supplementary, so half of it plus this one equals to 90 degrees, which means pi over 2, right? So we just derived from 1, 3 to 2, 4. Now let's look at, actually 1, 4 to 2, 3, that's the similar thing, okay? Now let's look at the definition of the harmonic quadrilateral. So ABCD is a cyclic quadrilateral. This is condition set, right? ABCD is a cyclic quadrilateral. If AB times CD equals to AD times BC, then we call ABCD harmonic quadrilateral. And later on, we will see why we call it harmonic quadrilateral. Okay, just use this first. If AB times CD equals to AD times BC, right? Now let's see this one, property 1. ABCD is a cyclic quadrilateral of circle O, then PA, PC are tangent to circle O and PBD are collinear if and only if ABCD is a harmonic quadrilateral. Okay. The problem is like this. So we have a circle O here. And we find a point P here, right? We find two tangent line. We call it AC, that's tangent point, right? This is BD. So if now we see that PBD are collinear, right? If PBD are collinear, then quadrilateral ABCD is a harmonic quadrilateral. So that means we want to prove AB times CD equals to BC times AD. Basically, we want to prove that AB to AD equals to BC to CD. right? Which is true because AB to AD, AB to A, because triangle PAB is similar to triangle PDA. So AB to AD equals to PA to PD. And for here, because the triangle PBC is similar to triangle PCD, so BC to CD equals to PC to PD. And because PA and PC are the tangent line from the same point, that means PA equals to PC. So PA equals to PC, these two are equal, which means this is valid, right? This is valid means ABCD is a harmonic quadrilateral. So let's consider the next thing that if this quadrilateral, if ABCD is harmonic quadrilateral, then we want to prove that PBD are collinear. But for the figure, we just do the similar drawing here. It's easier. Okay, AC here, P is here. Now we know that I just draw it look like this. Okay, so we won't be confused. So if I draw it look like this, right? It's on a different point. So we call this as B, this as B prime. Okay, based on the first one, we know that if we connect, actually let's call this one B, this one is D, right? So we fix this. So D is here, D prime is here. Basically what I did is that, let's assume that the PBD are non-collinear, right? And ABCD is a harmonic quadrilateral. So PBD are non-collinear, which means that I can extend PB, intersect the circle O on another point called D prime, right? D prime would be different to the point D. But for the first thing, we know that in this case, if PBD are collinear, then we get AB times CD prime equals to AD prime times BC, right? That's what we get from the first one we just proved. Then we already know that ABCD is a harmonic quadrilateral, which means AB times CD equals to AD times BC, right? That is saying we know that AB to BC, which is a constant, equals to AD prime to CD prime equals to AD to CD. Right? Now we want to prove that if this is true, then D prime has to be the same point as point D. So let's connect AC. Consider what is AD to CD or AD prime to D prime, CD prime. That is saying we can just find a point on the arc AC, right? And calculate for this ratio, which is sine angle for AD prime to CD prime. That is a sine angle ACD prime to sine angle CAD prime, right? Now we consider about this point that moving from this D prime point, moving from point C to point A, right? While it moving from point C, it starts from point C, that make angle ACD to be 90 degrees at first, right? To sine angle ACD, to sine angle ACD prime, which is 0, which means we start from infinity and gradually or say monotonically decreasing it to 0, right? Because once it on this point, then sine angle ACD prime, that's 0, and sine angle CAD prime, that's 1, right? It's monotonically decreasing, which means that if this is true, then D is a single point. Okay, that's for the property 1, and let's see the property 2. Property 2. ABCD is a cyclic quadrilateral of circle O. P is any point on O. PA, PB, PC, PD is a harmonic bundle if and only if ABCD is a harmonic quadrilateral. Right? Actually, that's why we call ABCD a harmonic quadrilateral, because any point on the circle O connected to PA, PB, PC, PD, we get a harmonic bundle. Right, so we call it harmonic quadrilateral. Let's prove it. So first we have circle O here, and say we have A, B, C, D here. Right, and we have point P here. We connect PA, PB, PC, and PD. Right, so we're saying that we want to prove if AD times CB equals to DC times AB, then PA, PB, PC, PD is a harmonic bundle. Right? So if we want to prove that PA, PB, PC, PD is a harmonic bundle, then we just need to prove that the sine angle APB to sine angle CPB equals to sine angle APD to sine angle CPD. Right? PA, PB, PC, PD is a harmonic bundle is equivalent to this one. That's PA, PB, PC, PD is a harmonic bundle. Okay, equivalence to this one. So basically we want to prove that if AD times, we want to prove that these two are equivalent. Right? So what is AD times CB equals to DC times AB? Right? We have AD here. We have CB here. Right? So CB can be rewritten as, so AD can be rewritten as (2R) sine angle ABD, right? And we know that sine angle ABD equals to sine angle APD, so it equals to 2R sine angle APD. That is AD. And CB equals to 2R sine angle CPB. Similarly, DC equals to 2R sine angle DPC. And AB equals to 2R sine angle APB. Right? So AD times CB, that is 4R squared sine angle ABD times sine angle sine angle APD times the sine angle CPB. And DC times AB, That is 4r squared sine angle DPC times sine angle APB. So it's obvious if we use this one equals to this one, so that means this one equals to this one, 4r squared cancels, so we have sine angle APD to sine angle CPD equals to sine angle APB to sine angle CPB. Right, vice versa. So that means if ABCD is a harmonic quadrilateral, then PAPB-PCPD is a harmonic bundle. Or if PAPB-PCPD is a harmonic bundle, then ABCD is a harmonic quadrilateral. Okay, great. We just covered the topic of harmonic bundles, which you will find very interesting and useful when we talk about the conjugate median. Okay, I hope you like this video. See you in next one. Thank you.